An overview study on 2.4 GHz CyFi Transceiver CYRF7936 Cypress Semiconductor. Welcome to this training module on the CYRF7936 2.4 GHz CyFi, where you will be introduced to a wireless USB technology and the CYRF7936 2.4 GHz CyFi device features. Wireless technologies have gained rapid acceptance in the marketplace, and the growth continues to accelerate. The ability to move data without having to connect a cable, run wires, or worry about having the right adapters is very appealing. Wireless offers the promise of convenience, speed, and ease of use. Wireless is still all about moving information from point A to point B. Depending on the needs of the application, data may move in one direction only, or it might need to move in both directions. There are many different wireless technologies in use and emerging today. Examples include Wi-Fi, Bluetooth, Zigbee, ultra-wideband, and many more. These technologies differ in many ways, such as frequency spectrum, data rates, data encoding, protocols, network topologies, and others. The Cypress wireless USB and PROC products are aimed at mid to low data rates, up to 1 megabit per second, and simple cable replacement or simple network topologies. Wireless USB only supports moving data in one direction at a time, thus it is considered half duplex. Here are some differences between wireless USB and 27 MHz technology. Here is a comparison between wireless USB and Bluetooth technologies. The CYRF7936 IC is designed to implement wireless device links operating in the worldwide 2.4 GHz ISM frequency band. It is intended for systems compliant with worldwide regulations covered by the ETSI EN 301-489-1 v 1.41 spec, the ETSI EN 300-328-1 v.1.3.1 European spec, the FCC CFR 47 Part 15 USA and Canada, and the TELEC ARIB T66 March 2003 for Japan. The CYRF7936 contains a 2.6 GHz CyFi radio modem, which features a 1 megabit per second GFSK radio front end, packet data buffering, packet framer, DSSS frame baseband controller, and receive signal strength indicator. The CYRF7936 features a SPI interface for data transfer and device configuration. The CyFi radio modem supports 98 discrete 1 MHz channels. Regulations may limit the use of some of these channels in certain jurisdictions. Here are some target applications. This device fits applications requiring wireless connectivity. The CYRF7936 contains a 2.4 GHz CyFi radio modem, which features a 1 MHz GFSK radio front end, packet data buffering, packet framer, DSSS baseband controller, and receive signal strength indicator. A CYRF7936 features a SPI interface for data transfer and device configuration. The baseband performs DSSS spreading and despreading, start of packet, end of packet detection, and CRC16 generation and checking. The baseband may also be configured to automatically transmit acknowledge handshake packets whenever a valid packet is received. This transmitter uses a DSP-based vector modulator to generate an accurate GFSK carrier. The receiver uses a fully integrated frequency modulator detector with automatic data slicer to demodulate the GFSK signal. Data is converted to DSSS chips by a digital spreader. Despreading is performed by an oversampled correlator. The DSSS baseband cancels spurious noise and assembles properly correlated data bytes. The DSSS baseband has 3 operating modes: 64 chips per bit, single channel, 32 chips per bit, single channel, and 32 chips per bit, single channel dual data rate. Here explains functional blocks of the device. The device includes a 2.4 GHz CyFi radio modem, a frequency synthesizer, a baseband and framer block, a SPI interface, interrupts, clocks, power management, and a receiver front end. The CyFi radio modem is a dual conversion low IF architecture optimized for power, range, and robustness. It employs channel-matched filters to achieve high performance in the presence of interference. An integrated power amplifier provides up to plus 4 dBm transmit power with an output power range of 34 dB in 7 steps. Before transmission or reception may begin, the frequency synthesizer must settle. The settling time varies on the channel. 25 fast channels are provided with a maximum settling time of 100 microseconds. The fast channels, which are less than 100 microsecond settling time, are every third channel, starting at 0 up to and including 72. For example, the sequence 0, 3, 6, 9, all the way up to 72 are the fast channels. This slide is a continuation to the previous slide where we explain packet buffers and radio configuration registers, interrupts, and receiver front end. Here explains the data transmission mode employed in the CyFi radio, and also the data rates supported by this device. This slide we have shown the packet frame in which we have a start of packet, packet length, followed by payload ending with end of packet, and CRC16 for error correction. Here we explain the features of the auto transaction sequencer. The CYRF7936 IC provides automated support for transmission and reception of acknowledged data packets. When transmitting data in transaction mode, the device automatically starts the crystal and synthesizer, enters transmit mode, transmits the packet in the transmit buffer, transitions to receive mode, and waits for an acknowledge packet, transitions to the transaction end state when an acknowledged packet is received or a timeout period expires. Wireless USB LS utilizes a 2.4 GHz direct sequence spread spectrum radio interface. DSSS generates a redundant bit pattern for each bit to be transmitted. This bit pattern is called a chip or a pseudo-noise code. Because they use direct sequence spread spectrum technology, wireless USB systems encode their data within pseudo-noise codes. The main advantage is to increase the robustness and recoverability of the signal in the presence of interference. A simple explanation is that a single data bit from the application is represented by multiple data bits when sent across the air, and decoded back into the original data bit on the other side. One result of using pseudo-noise codes is that the devices in the given network must agree to use common pseudo-noise codes in order to understand one another. Another advantage of this is that it increases the co-location capabilities, since the devices can share the same channel if they use different pseudo-noise codes. The pseudo-noise code is a binary signal that is produced at a much higher frequency than the data that is to be transmitted. Because it has a higher frequency, it has a large bandwidth that spreads the signal in the frequency domain. The nature of this signal makes it appear that it is random noise. The wide bandwidth provided by the pseudo-noise code allows the signal power to drop below the noise threshold without losing any information. This allows direct sequence spread signals to operate in noisy environments and reduces the interference caused by traditional narrowband signals. In the presence of interference, the transmitted pseudo-noise code will often be received with some pseudo-noise code chips corrupted. The receivers use a data correlator to decode the incoming data stream. If the number of chip errors is less than the correlator error threshold, the data will be correctly received. Otherwise, the data bit will be marked as unknown, and the software error recovery mechanism will be used to recover the unknown data. In the wireless USB protocol, pseudo-noise code is a 1-byte number index into the gold code table. Changing the receiver's pseudo-noise code is equivalent to changing the 32-chip or 64-chip pattern that the receiver is trying to look for. This slide shows a microcomputer interface with this wireless USB device and a sequence diagram. The 4-wire SPI communications interface consists of master out slave in, master in slave out, serial clock, and slave select. The SPI receives the serial clock from an application microcomputer on the S clock pin. Data from the application microcomputer is shifted in on the master out slave in pin. Data to the application microcomputer is shifted out on the master in slave out pin. The active low slave select pin must be asserted to initiate a SPI transfer. The RSSI register returns the relative signal strength of the on-channel signal power and can be used to determine the connection quality, determine the value of the noise floor, and check for a quiet channel before transmitting. The internal RSSI voltage is sampled through a 5-bit analog-to-digital converter. The converter produces a 5-bit value in the RSSI register along with a valid bit. Once a connection has been established, the RSSI register can be read to determine the relative connection quality of the channel. To check for a quiet channel before transmitting, first set up the receive mode properly and read the RSSI register. Then, wait greater than 50 microseconds and reread the RSSI register. Next, clear the carrier detect register and turn off the receiver. The RSSI register value between 0 and 10 indicates a channel that is relatively quiet. An RSSI register value greater than 10 indicates the channel is probably being used. An RSSI register value greater than 28 indicates the presence of a strong signal. The ISM band is a busy spectrum with a lot of different technologies sharing the band. Therefore, managing interference is an important consideration. The DSSS technology itself is the first stage of managing interference. In the presence of strong interference, the DSSS technology by itself may not be enough to overcome interference. There are other mechanisms for overcoming interference. The first is detecting the interference, which can be accomplished by monitoring the background noise level using the measurement of signal strength. Once interference has been detected, the system must then identify a channel with an acceptable level of interference and then move all nodes on the system to this new channel.